This is where we left off. When the circuit turns on for the first time and all the inputs are 0, what's the state of Q and Q naught going to be? Remember, we talked about that and how we couldn't really tell. If everything happened at the exact same time in this like beautiful ideal scenario, it would constantly like forever just switch states. Forever, right? But we know that in practice, one set of transistors and the other set of transistors, things will happen at a slight different time. Therefore, one set, Q or Q naught, will get set first, and as soon as they're out of sync, it's stable. Or it will become stable, right? So that's what we explored. Okay, now the D latch. The SR latch can be modified very slightly to eliminate the ability for both set and reset to be high at the same time. Remember how I was showing you up here? Okay, there was the error here. These should both be 1. But this is like the undefined state, right? We don't want to set and reset at the same time. What would that even mean? There's no utility in that. So how does it even behave in the circuitry? Well, it kind of gives us some nonsense output where somehow Q is 0 and not Q is also 0. It was nonsense, right? So we can fix this very simply by taking an SR latch and connecting the inputs, but having it be not the other. You either set or not set, okay? Now, you will note, though, that this then loses the ability to give it nothing, right? With this design, S and R must be the opposite of one another, no matter what. Where here, we did kind of like the state of neither high, because then it just left everything alone. But all right, we'll have to come back to that later. So that's a little bit of what we're losing. But here, we've got a new design where S and R still like exist, but it's connected to one input. If this is high, if we want to set, okay, set, reset will be low. If this is 0, set is 0, but reset is high. Which, think back to how the SR latch worked. Remember, when S is high, we want Q to be high. When R is high, we want it to be set to 0. When this is high, we get like 1 in Q. When this is low, 0, 0, 0 switches to a 1. R is high, it resets the output. So it's like the data. Do we want the data to be a 1 on? The data stored in Q to be a 1 or a 0? On or off? That's the idea. This is called a D latch. So let me make sure I didn't miss any here. SR latch can be modified to eliminate the ability for both set and reset to be high at the same time, make it such that only one can be active at a time. This can be achieved by having a single input split into 2 signals. One is fed, one of the 2 parts of the split signal is fed into the SR latch. The other part is inverted before being fed into the SR latch. That's it. So there. Any questions about what we're seeing here? It's clear? Happy? All right. The above figure shows an SR latch may be modified. The D means data. So this is a D latch, a data latch. Do we want to set it to a 0? Do we want to set it to a 1? If it's a 0, R is set high, which means we reset the output Q to be 0. When it's a 1, reset is 0, set is high, and so Q is 1. With a configuration, though, it's not possible to have S and R both be high at the same time, or at least the inputs that were S and R, yeah, whatever. Unfortunately, but we also lose the ability to have S and R both being low at the same time, which did have value for us, right? That was like a leave it alone state. I'm doing neither. Right? this state where they're both 0 is called like the quiet state of an SR latch. It's just we're doing nothing with it, which is ideal. We want to be able to like leave it alone. So we can fix this problem by adding a new little feature. But before we talk about that, do we have, last chance, any questions about this D latch? So to be clear, we've eliminated that nonsense state of both being high, but we've also eliminated the quiet state, the ability to have it do nothing. We can re-add that functionality. We could re-add the functionality of leave it alone, do nothing. But we're going to do it in a slightly different way than having both inputs be 0. I mean, it effectively is kind of having both inputs be 0, kind of, but you'll see. All right. So to store the data latch needs a way to enter the quiet state. So what I mean store is I want to be able to set the Q value to high or low. Let's go back to the SR latch. If I set it, Q becomes 1. And if I want to store that data forever, I just set S and R to 0. And Q will remain 1. It's stored. The only way to like store the data here is to set data to like, if I want to set Q high, I have to set data high and leave data high. I'm not really storing anything. That's just, if D is on, Q is on. If this is off, Q is off. I've stored nothing. I've effectively come up with like a relay of what's the output of this with a lot of extra steps. It's a waste of time. I'm not storing anything. So I need a way to have it go back to its like quiet state, where I can set it and then forget what this is, and that doesn't change. That's what I want. Is my objective clear? So how do I do this? We just add an enable, another toggle, okay? In other words, there needs to be a way to allow S and R to be 0 at the same time, allow S to be 1 and R being 0 or vice versa, and disallow the ability to be R, right, okay, going back to what we really want. This can be achieved with an enable. Input that can deactivate the NOR's inputs. If the enable is on, relay the value of S and R to the NORs. If the enable is off, do nothing. So here, look at this circuit. Take a moment, I'm going to give you 30 seconds, look at it and understand what it's doing. If it isn't obvious, the part that's new is this part with the ands and the enable. This part's the same, skipping the ands, and this is the SR latch. But it's this enabling the AND gates that's new. So take a moment, look at it, and make it make sense. Okay, for a moment, I want to check something here. Open a D latch. Okay, perfect. So I want to be clear about what I mean about not being able to store data. Notice how whatever this is, I can't set it high and then leave it alone by like toggling, like no. D and Q are just, they're connected. There's no way to, if I took like a probe and said, what's the value of Q? It's always the same as D, no matter what. I can't set a value, put it into Q, and then carry on elsewhere because this It's just extra steps of what D is. It's nonsense. So D with enable. So what's going on here? So again, first, recognize that this part here is an SR latch. This part, like the R and the S with the data going straight to S, ignore the AND gate for a second, and the inverted going to the reset part. Okay, that's the D latch. But what's going on here? We've got this enable. AND gates with a separate input to them, like this, a design like this. This is such a common design to basically turn on or off whatever this is. Okay? Think back to the multiplexer. Whatever this signal is, if I select it, it's like enabled. Just if that's not clear, don't think too hard. Let's go simple. I don't care whatever D is. If enable is 0, false and whatever is what? If enable is high, true and whatever is whatever. So this could be high or low, it doesn't matter. Either if this is on, whatever the value is here is relayed. If it's a 0, it's a 0. If it's a 1, if it's a 1. And if this is a 1, this would be a 0. If this is a 0, this would be a 1. Okay? That's the idea. So this now gives us the quiet state. But we don't have a quiet, like, we didn't really ever get a quiet state by having like R and S be set to 0. I mean, we kind of did by these AND gates though. Like the two inputs to this part of the SR latch are 0 now. So we've allowed the circuit to have a quiet state and completely eliminated the ability to have both high at the same time, which is great. So if enable is low and Q is high, but remember, what's the state going to be? It's kind of a roll of the dice, right? So Q is high. It doesn't matter what's going on here. Q doesn't change. If I turn on enable, well, it's immediately going to go low because this is 0, and a 0 gets stored. Let's hit pause for a second. We talked about SR latch. Think about the data latch. I want to store whatever value is on D. Okay? D was low when it was enabled. Q never changes. I set D high. I disable. Q never changes. If I leave it high and I do this, well, Q is just going to keep changing. This is what we wanted. And there's no way to get to that weird, undefined state of set and reset high at the same time, and Q not being 0 at the same time, which made no sense. So now we have a data latch with enable. Or sorry, a D flip-flop. Pardon me, it's not a latch. A D flip-flop, no, latch. It's not a flip-flop yet, my goodness. A D latch with enable. Great. We now have the ability to store data, which is really cool. Any questions about what we're seeing right here? Yeah?
So do SR latches get used at all?
Oh, they're going to have a lot of use cases in like circuit design in general, but where we're headed, I mean, yes, in the sense that it's right here,
yeah,
right? But like as a functional unit, yeah, they're there. And in fact, if we go here, component, flip-flops. Okay, flip-flop is a little different. We're going to talk about flip-flops soon, but there's they call it an RS, it's SR. You might remember I said set, reset, set, whatever you want to call it. Yeah, there you go. And there's a D, a T, I don't even know what that is, a JK, that's kind of a cool one. Anyways. Yeah. Any other questions or anything? All right. So now D, flip-flops. So raise your hand if you've ever heard. So I like to teach my courses in a way where we like discover everything as we go. And that's still the goal with this course. It's not, sometimes it's a little tricky because we kind of know where we're going. Like we know stuff about how computers work, right? And so I'm assuming most of you have heard about like a clock. And I don't mean like a clock, I mean like a computer clock or something, right? Like, oh, the frequency of my computer is like 2 gigahertz or something, right? Like you've heard this before, right? So what does that mean? Well, everything in your computer that needs to be synchronized is synchronized with a clock. There is something in your computer that very predictably and periodically goes like, everything happening in your computer happens at this speed, okay? Like data gets there, then there, then there, number crunch, there, move to there, stored in RAM, put over there. Everything happens at this frequency along with this clock. Some parts of the computer which aren't dependent on being synchronized or whatever, fine. But a lot of what we do is synchronized based on a clock. Like I can have, if I go back here, okay, enable, disable, right? Let's say I'm enabling this. It's enabled, and data's changing on here, okay? But like the data coming in, this is a signal line that's connected to who knows what, all right? Can you see that? Yeah, okay. I really don't want anything, like there's an enable, there is a data line, but really, if I have any data that I want to get in there, it's like I want like a second enable line that is like on a clock pulse. But like a clock pulse, so here's a clock pulse, high, low, high, low, high, low, high, low. But like, it's interesting, right? Like if I have an enable though, and data's here, and I want to get it set, and then like the data here changes. Okay, I'm trying to come up with a good example to explain this, and it's a little tricky. Imagine the clock signal was hooked up to enable. When the clock is high, I want to be able to store the data, okay? Right? So clock signal goes high, I store the data. And we gotta wait a moment for the clock signal to go low, right? Look, our clock speeds in our computer are like on the order of billions of ticks a second, right? Like it's a lot. But let's say this is like 1 second, 1 second, 1 second, 1 second. Okay, let's say it's a one second thing, right? When this signal is high, and that's an enable, I can't ever change what's on this signal line, because this signal line might be hooked up to who knows what, okay? I can't change what value's in there when this signal is high, right? Because if I do, it's going to change the signal there. So really what I want to do is have the ability to store data, but I only want like that storing. I don't want that storing to happen any moment when this enable is high. I want to have it happen at the instant there's a clock pulse, such that like enable is high for like the tiniest bit of time where, okay, data's set, enable. Like when I say enable, I mean enable, disable really quickly. It gets stuck in there. That's really what I want. But a clock pulse is like low, high, low, high, low, high. But really, the moment I go high, I want it to latch in there. That's the goal here. And it's a great way to synchronize what on earth is going on inside the computer. All right, so a clock is a device within a computer used to synchronize most of the components performing operations. Some components don't really need a synchronization, some of them definitely do. It produces a periodic waveform at a constant frequency, jumping from low to high to low to high, etc. For those of you, be honest. If I say like 1 hertz, raise your hand if you know what that means. Okay, so we'll explain it. A hertz is a unit that means per second. That's it. So if you have something that's like 1 hertz or 1 per second, we have one thing happening per second. 1 clock pulse, 1 cycle per second. If you have something that's like a kilohertz, that's 1,000. A megahertz, that's 1,000,000. A gigahertz, that's 1,000,000,000. So if your computer's running at like 1 gigahertz, you're getting 1,000,000,000 cycles per second. That's what that means, FYI. It's an interesting unit because, like, you know, everything's always like like speed is like meters per second or something, right? So there's always like a unit divided by something, but a hertz is always like the thing per second. It's kind of neat. Anyways, doesn't matter. Named after somebody named Hertz, I'm guessing. I don't know. All right, so typically one wants to synchronize when the data is stored in latches with the clock cycle. A simple solution to this is to use the clock signal as the enable signal for the D-latch, like I was just saying. However, the D-latch with enable will change the value stored whenever the enable is high. All right? So what I mean is, like I showed you, let's restart this. Okay? Data's changing, data's changing, data's changing, data's changing. Enable goes high. Data's changing, data's changing, data's changing, data's changing. Enable goes low. Data's changing, like think of that enable as the clock signal. Okay? And you know what? For fun, let me do something wild here for you. Check this out. We can go to here, components, IO, clock. If I right-click this, I can make it a real-time clock happening at once a second. So watch. So it literally is a clock. Really what I want to achieve here is not when the clock is high do I want it to be enabled. Really what I want is the instant, and only for that instant that the clock goes high do I want it to actually be enabled. Okay? That's really what I want to achieve. All right, so one solution to this problem is to combine 2 D-latches in series, but carefully control when the D-latch is enabled. So, this design right here, although what do I have? Yeah. So, I think it's probably best if I give you another 30 seconds a minute to look at this and think about what's going on. But before I do that, let's point out that what we see right here, this is a D-latch with enable. Okay? This is a D-latch with enable. But notice that the enable is hooked up to a clock. And notice that the clock signal is inverted on this one and goes straight to that one. So we've got there. So take a moment and think about what this would do. And another hint I'll give you is try not to think like, okay, when this is there and that AND gate and this, and then if it flips to that. Don't do that. That's a waste of your time. Think more abstractly. We've learned about what a D-latch is with enable. Think, okay, based on how a D-latch with enable works, what would happen here? Take a minute. Okay. Let's ignore this one for a second. This is an enable signal. Comes to here, set, reset. It's just the D from the data latch. Okay, so pretend there's like data here, that D toggle we had before. When the signal goes high, whatever value is here gets latched in to the Q. We can ignore Q naught here, it doesn't really matter. In fact, we ignored Q naught here because it didn't really matter. We could ignore that, right? If the value here was a 0 and that clock enables it, we get the 0 in Q. If it's a 1, we get a 1 in Q, okay? That part's not really new. But we've got this thing here. Now, the value, so this is only ever enabled when that one isn't, because the clock is like this, okay? So let's say the clock signal is low, meaning this latch is enabled. This D can be flipping to whatever. And then suddenly, that clock signal changes such that this one gets deactivated. But the value that was last here gets latched in. And this one gets enabled, and the value from here actually gets set. Let's D-latch, D flip-flop. Here we go. There. Let's have fun. So first of all, okay, here. When you load up a clock component, by default, it's just something that you click to cycle. You might be like, well, what's the difference between that and an input? Nothing really in this state, but you can go here and change to a real-time clock, and you can set its frequency to whatever. I know there's a drop-down list, but you can set it to like crazy numbers if you want. All right, cool. All right, so here we go. I can keep doing this. I guess I'm doing it too fast such that nothing's ever going to change. Let's go back to this here to make it real-time clock. Okay, so clock is low. Whatever data is, the state of Q, think of this as a whole thing right now. The state of Q doesn't change, right? But let's set, okay, we'll set it to 0. We enable this, and look, whatever value is here, come on, there. There, boom, the 0 went there, okay? But again, look, the clock is enabled, right? That enable signal is high, but Q can never change. And in fact, the state here, like, why can Q never change? Because the value of this latch can never change. The value being output by this latch can never change. Why can the value of this latch never change? And when I say this latch, I mean the input to this one, the output of this one, right? So this line here is 0. Why is it 0? Why can it never change when I do this? Because the whole thing is disabled because it's not clock. Cool? I think this is pretty cool. This is a common design for a flip-flop. It's called a flip-flop because it goes with the clock. Flip-flop, flip-flop. There are other designs that can work. You can do things called like edge detection circuits, where you really do look for that instant. Like you can build circuitry pretty simply. It's just you took electronics, right? If I were to ask you, I'm putting you on the spot. If you don't know, it's entirely fine and reasonable that you don't know. But what kind of circuit would I use for edge detection? It would be a filter, effectively, an RC circuit. That's all it would be, a resistor capacitor. You would do a filter to check for like a very quick pulse, and you would let a high frequency change through, effectively. Anyways, doesn't matter at all. I just wanted to put them on the spot, to be mean. Where you basically build circuitry where the enable will really only be high for like this tiniest instant here. And depending on which capacitor and resistor you use, you could actually specify, like you could find like a time duration to align with your clock speed of your circuitry. So you could build a really simple like circuit like this. I might have it backwards. I can't remember. Anyways, you would build a very simple circuit with a capacitor and a resistor. These might need to be like that. I can't remember. Anyways, it doesn't matter. You can design flip-flops other ways, but this is a common design that uses nice like solid-state circuitry. I will warn you though. Does anyone know what this design is called? Do you know? Yeah, it's got like a bit of an antiquated name, let's say. So the only reason I'm giving you a heads up, if you go and you're like reading and you're like, oh my, yeah, that's what they called it. And so we're kind of, there you go. Anyways, this is our flip-flop. Cool? I think it's pretty cool. And you might say, that feels like a lot of steps. Kinda, right? We've got a D-latch and a D-latch, but a couple of gates. I think it's pretty clever to me. The whole point, the whole reason this works is when this one is disabled, this is the cue we really care about. When the clock is low, this latch, this D latch, is disabled, meaning the value of this can never change. But the value of this can change a bajillion times, I don't care. But the moment this goes high, which it is now, this latch gets deactivated, meaning the value here can't change anymore, and the value here is what leads into this circuit, the D value, meaning it can change, but it can only ever change based on what this was, not what this currently is. And this could be flashing a bajillion times, it doesn't matter. I think that's pretty cool. Questions, thoughts, concerns, comments, anything? This right here, yeah.
Do you have to have a not Q output?
No, it's entirely, there is, but one could be, no. There could be value in it for what you're building. It's interesting that whatever, you might say, well, there's no utility to having that. Yeah, you're right. If there isn't for what you're needing it, then you don't have it. But it is interesting to note that the output of this gate right here is always going to be the opposite of this. And if you need to know what the inverted output is, then it's good to have. Now, when thinking of circuitry, depending on what you're designing, remember, when this is a 0, it's sunk to ground. So if you really wanted your circuitry, if this was like Q naught, and this is Q, okay, maybe you have like a voltage source and an LED or something, okay? Right? So when Q is high, like, okay, there's data in there. And this LED would go off because we have something connected to ground through a high voltage source. Like basically, you connect this little light bulb to ground, thereby enabling it. So suddenly, I'm getting utility out of having something connected to ground. If that feels contrived, I am using it as an example, but this wouldn't be that crazy of something to do. So often there is utility in having like, okay, whatever. And you could say like, but you could just redesign your circuit. Yeah, probably. I could use a NOT gate if I really wanted it. Yeah, but then I need another gate. But for our needs, no, we don't really care about the Q naught for us right here. But good question either way. To be clear, the question was this. Do I care? No. And why don't I really care here? Because if I really did care, if I know Q, I know Q naught. Right? Right. All right. In the above figure, C is labeled for the clock signal, which is serving as an enable for the D latches. Notice how the clock input is inverted before being fed into the first D latch, but not before the second. Only one will be enabled at a time. One is always going to be in the quiet state. And this is just explaining what we just talked about. But I'll read through it just in case I missed something important. The first D latch is active and can store whatever is on the D input when the clock signal is low. The D input can toggle several times, which would change the first D latch's output. The second D latch in the quiet state, meaning that the output value does not change based on the output of the first one. In other words, the value of D does not affect the value of Q and not Q. When the clock signal transitions to high, the first D latch enters the quiet state, meaning that the last value of D was latched in. The second D latch becomes active, latching the value being output by the first D latch. At this time, D can change, but will not impact the stored value on the first, as the first D latch is disabled, and thereby not allowing it to affect Q naught. With this configuration, the value of D can never directly alter the value of Q and not Q. It has to go through that first D latch. Pretty cool, right? Now here is a D flip-flop signal in digital. It's got a data input, a clock, a Q, and a Q naught. That's it. This is a D latch. This D latch is our most basic circuitry for storing data. "14 people here right now." Yeah, so this can store 1 bit of information, right? Now, we talked earlier this week, what if you want to store 8 bits? Well, just take 8 of these things and chain them together. You can only have 1 bit on one signal line at a time. So if I want 8 bits, I need 8 signal lines. And so I could just have 8 signal lines going into 8 of these guys. And we're all set. The triangle at the clock. Oh yeah. By the way, as per convention, a little triangle like this, that means clock. And you're like, but it's already labeled with the C. Yeah, but it means a clock, which I think is kind of neat. Sometimes in designs, depending on what you have. So by the way, this right here, if you go look at a D latch, no, D flip flop images. This right here is a common design. And here's like an SR latch. Here, look at that. Here's a D flip-flop. This is cool. Here's a D flip-flop with that. I was right about the configuration of the capacitor and resistor. You should be really impressed, by the way. Here's a flip-flop that uses like that edge detection, edge trigger D flop, which is pretty cool. Not overly important. I don't even think we can add capacitors to our designs in digital, and that's fine. That would be a high-pass filter. Only high-frequency changes could ever go through. That's all. I'm not going to explain why. It makes perfect sense, but let's not worry about it. It's because, no, let's not worry about it. But this right here, when it comes to a symbol, I lost it. Whatever. Sometimes the symbol is a little bit more elongated, and then Q and not Q. It's common to not have clock even labeled with the C. It's just a little triangle means it's a clock. So you might see something like that. Yeah. Yeah. Any last questions about this little D latch? This D latch is magical. It stores data for us. It is our basic unit of memory. That's it. Now, I will say, when it comes to how the memory on our computers that like we use every day, like our desktops, that uses something called like dynamic RAM, like DRAM. And this is like static RAM. Now, static RAM is like, so DRAM has some limitations and it works in a very interesting way. Basically, it uses a lot of capacitors that's like scanned to give like a charge or not a charge to update. There's a lot of weird functionality going on in DRAM. But DRAM is like a hack that's like inexpensive. This type of RAM is like better, but far more expensive to implement. You can get static RAM, but it's like really expensive and kind of unnecessary. We've got like another way to do it today. That's like we're kind of like cheesing it a little bit, but it works great for us and it's way less expensive. But this is RAM. Cool? This is like, yeah, and it's not like we have a new better way to do it. It's not really better, it's just cheaper. That's all. SR latch without enable, with enabled flip-flop. Cool, we covered them all. Nice. All right, registers and RAM. So D flip-flops allow one to store a single bit of information. However, they always update what's stored on every clock pulse. In many cases, one wants just a little bit more control. Like, at the end of the day, if I go back here, we still have, like, look, a moment ago, we looked at the D latch, not the flip-flop, the latch, which had an enable, which had, and a disable. When we disabled it, nothing changed. This one, there. This one, it's going to change depending on, wow, I'm getting really unlucky. There we go. Like the clock is always changing, meaning it's like, it's still now reacting to the value on D. I still want a way to be like, okay, but what if I want it all to be in the quiet state, meaning just completely ignore D, right? Before we looked at the clock, I had that enable thing. When it was set low, it didn't matter what D was. Nothing changed. But now clock is there, and clock is half the time high, half the time low, meaning it's enabled half the time. I still want a way to say disable everything. There are a lot of ways to do this. I could effectively do like this AND gate thing with the D again, right? Where whatever the D is, but I can AND it with like another enable signal. That's fine. You might say, well, do that same thing with the clock, right? Put an AND gate here with the clock, and when that signal is low, the clock is ignored entirely. And when it's high, we listen to whatever the clock is. You could do that. But as a very important rule to follow, never mess with the clock signal. Never, ever, or at least avoid putting your clock signal through any additional circuitry. You want your clock to get to every like thing that requires the clock as like unadulterated as possible. Because every time you add like a gate here, imagine there was a gate here, and that gate takes a nanosecond to change its state. Suddenly that clock signal is a little bit out of sync, right? You might say it's a nanosecond. Well, look, when your computer's running at 5 gigahertz, kind of matters, right? Suddenly things can get a little out of whack. So we got to be careful. So just right now, this is going to be warned to you several times. Don't mess with your clock signal. Don't disable your clock signal. There's like one rule. You can disable your clock signal if you're disabling your clock to your whole circuit to be like, okay, you are off now. Otherwise, don't mess with the clock signal. Otherwise, things can get out of sync. If you're to do that in digital, it would be fine. It's an idealized situation. It doesn't really matter. But, you know, don't mess with your clock signal. Anyways, in many cases, one wants even more control over when the data is stored, like we had. So, registers. There. A register is effectively, like I said, there are several ways we can go about doing it. But this is how we're going to do it. What we're going to do is say, what is this? Is it a multiplexer? Yeah? Multiplexer? Yeah. So this is our select pin. It's a 2-bit, we have a 1-bit, a 2-signal, 1-bit selector. When enable is low, this signal is fed into the register. When the enable is high, this signal is fed into the register. Well, this is the data one, so what's the other one? Well, it's itself. It's being fed back into itself. That's going to be the design. But we're going to stop here, and we'll pick up here whenever the next class is.